Madam, we will go for next 15 minutes is there. Good afternoon.
Hello?
Good afternoon, madam.
Are you listening? Hello, good afternoon. How are you?
Fine, madam.
Thank you for your invitation.
Welcome, madam. My pleasure. Madam, we will go for another 15 minutes is there.
Okay.
We can start 2 p.m.
Yeah, no problem.
Yes.
What is the background?
Madam, please unmute, madam.
Yes? Do you? I don't listen you.
Yeah. Fine, madam.
Now you have sound.
Yeah.
Yes?
Yeah, fine, madam. We will wait 10 more minutes, madam. Then we will start.
Sure. You have time.
Yeah.
Just to check if everything it was working.
Yes,
and
madam.
it is working.
Fine. Perfect.
Welcome to you all. Session will exactly start at 2 o'clock.
Good afternoon to all delegates and participants to today's session, second day session. Okay. You can check, sir.
Sound?
Close it. Madam, you are in.
Set the sound.
అది మేడం బయట అర్జున్ బయట అన్ని
Good afternoon to all delegates and participants. Welcome to today's session.
Just we will start within 2 minutes. It's okay. Madam, please unmute, madam. Sandra
Yes.
Penals, madam.
Yes,
Yeah,
I'm
yeah.
ready.
Yeah, now we are hearing. Just within 2
Okay.
minutes, madam.
Don't worry.
Yeah.
5 minutes, no problem.
Yeah.
Good afternoon to all the participants. After session completed, we will send the feedback form. Please fill the feedback form. It will close within half an
Hello,
hour.
good afternoon.
And if you have any queries, just post in Q&A. Don't post in chat box. If you have any queries, just interact with Sandra Pinales ma'am in the last session. Okay. Session will start in 2 minutes.
Okay.
వీడియో నాకు చేసుకోవద్దు ఎవరు నాదేనా
మీదే సార్.
It's mine. Yeah, it's mine. Again, it's coming. Unmute.
Yeah. Now exactly time is 2 o'clock. So we'll start this session. My warm welcomes to all distinguished speakers, Sandra Sinha Penales Madam, participants, and my dear colleagues for the second day of the 5 days International E-Seminar and Recent Research in Mathematics, ISSRM 2020, hosted by Department of Mathematics, School of Science, Geetham University, Bangalore campus. Okay, over to Shashikala Madam.
Good morning, good afternoon to all delegates and participants for the second day session. Myself, Dr. Sasikala, Assistant Professor, Department of Mathematics. Once again, my heartfelt greetings and warm welcome to everyone.
We now call upon Dr. Jogarao Gunda, Assistant Professor, Department of Mathematics, Geetham School of Science, Bengaluru, to introduce Professor.
Very good afternoon. Myself, Dr. Jogarao Gunda, Assistant Professor, Geetham University, Bangalore. It gives me a honor to introduce an eminent speaker and resource person, Professor Sandra Penales. She has born on 12th December 1970 in Lisbon, Portugal. She has completed her graduation and post-graduation in mathematical analysis with both University of Évora, Portugal, PhD in mathematics in 2007 from Azores University, Portugal. Professor Sandra has been working as a professor in Military Academy, Portugal from 2012, and also a senior researcher in SM Nikolsky Mathematical Institute of Rudan, Moscow, Russia from 2017. She worked as a professor. Professor Sandra has been working as a professor in Military Academy of Portugal from 2012 and also a senior researcher in SM Nikolsky Mathematical Institute of Rudan, Moscow, Russia from 2017. She worked as a professor in University of Azores from 1999 to 2012. She worked as a visiting professor in Munich University of Technology, Germany in the year 2006 and also Florida Institute of Technology, Melbourne from 2009 to 2010. Cyprus International University, Texas, United States of America, invited as a honorary professorship in mathematical science. Professor Sandra guided 9 PhD students, published more than 152 research papers in reputed international journals, highly impact factor in the area of difference equations and ordinary differential equations and oscillatory behavior and time scale equations. She has successfully completed 5 research projects to find the necessary and sufficient conditions of impulsive differential equations and understanding and modeling biochemical interactions of various pollutants with respect to marine toxicology, marine ecology, oscillatory criteria for differential equations. Professor Sandra is a good learner, referred more than 10,000 research articles. She has more than 460 citations. She has collaborated with eminent mathematicians all over the globe and maintaining a good relation in the area of research. She has served as a member of various international bodies, member of senior researcher in Rodan Mathematical Institute, Moscow, Russia, member of University Lisbon, Center of Mathematical Competition, member of Edor Education Lisbon, member of CIMAT Lisbon, Portugal, member of International Society of Differential Equations, member of CINAMIL Military, Portugal. She is an editorial board member of International Journal of Mathematical Manuscripts, International Journal of Mathematics and Computation, Contemporary Analysis and Applied Mathematics, Enlightenment of Pure and Applied Mathematics, Advances in Dynamical Systems and Applications, Journal of Computational Mathematics. Professor Sandra is an invited editorial board member of many international journals, in the area of differential equations. She is surveying a referee of 20 international top journals in various mathematical subjects. She has served as a scientific committee member of 30 international conferences in various countries all over the world. Professor Sandra attended and delivered her research experiences in 44 international countries in more than 22 international conferences. She organized 8 international conferences in various countries: Russia, Portugal, Philippines, and Turkey. She was the chair of 15 international conferences, symposiums, and seminars in Italy, Portugal, Germany, and Greece. She is an author of a book, An Introduction to Complex Analysis in Spencer series. She is editor of 136 preceding books. It is a honor to have a great mathematician and academician with us. Welcome, madam. Thank you, one and all.
Thank you,
very
Dr.
much.
Jogarao, for the introduction.
Now I request Professor Sandra Pinales to take over the session.
Thank you very much. First of all, I wish to thank the organizers for the invitation. Thank you very much for this presentation, introduction that you do to my person and to my work. It's a pleasure to be online with you. Of course, the wish is to be there with you, but it's not possible. All of us are living very hard moments with this pandemic. However, perhaps one day I can visit you and visit your institution. I want to thank to everyone that are online on this moment, and I will start now my presentation. Let me share here my screen. Here it is. Everyone see? Do you
Perfect,
see
madam.
my screen?
Yeah. Yes,
Okay.
madam.
Okay.
Yeah.
So I will start. On this work, I will share with you some results of 2 papers about the behavior of solutions for linear non-autonomous mixed type difference equations. So let us see what we will have. On this work, we will start to study this difference equation of mixed type. The different equations of mixed type are very important when we talk about applications. A lot of people do application about this method, about this equation, because when we have a mixed type equation, what we will have? We will have the past and the future. I have here the knowledge that I have the past events, and here what I wish for the future. And is when I put these 2 knowledge and wishes for the future in same equation that I can take a decision. Let us see what we have exactly on this equation. Here, P and T are real numbers, L and M are positive integers, and here we have the forward operator. Later, we will complexify a little more this equation, but for now, we will see this one. We will study now stability. Later, we will complex a little more, and we will study the oscillatory behavior. So this work is divided in 2 different parts. The qualitative theory of difference equations, it was studied by several scientists. For example, here we have a very known book from Professor Agarwal, Difference Equations and Inequalities, Theory, Methods, and Applications. We have an introduction to difference equations, a very important book in oscillatory theory from Giori and Ladas, Oscillatory Theory of Delay Differential Equations, from Peterson, Difference Equations, one introduction with applications, Theory of Difference Equations, Numerical Methods and Applications. As you can see, here we have very important people, very important researchers working on this method. This equation, it was introduced on this paper, oscillatory mixed difference systems, in 2006, and it was established oscillatory criteria for oscillatory behavior for this equation. Here, we will denote the set of all C, where Cn are real, and what we can say about this. This set C is a finite dimensional space with usual supreme norm. We will specify an initial condition, so I have a problem, and I will have the initial condition where xn is C of n for all n smaller than m until minus L. This because the delay and symmetric of advance, last advance. And a very important condition is the consistency condition. What must to happen? And all work as this in basis. The difference between C1 and C0, we have here the forward operator for this C sequence, it will be given by this expression. So we will consider C equal to 0, n equal to 0, and it is what we call consistency condition. Now, the solution of a difference equation, evidently, it will be a sequence of real numbers satisfying the equation for all integers where n is bigger or 0. To guarantee this existence and uniqueness, we must assume that Q1 is not 1 if n is 1. Q1, I remember, is the coefficient of the advanced files, and Tm is different of 0 if m is 2 or more. So let us start the asymptotic behavior study. The characteristic equation of this equation is given by this expression, 1 equal to lambda, and after we have here minus this sum minus this one. This is characteristic equation, and it's very important to study the asymptotic behavior. So we will say that the characteristic equation has the property A, and is very important, this property, because it will appear several times. We say that the characteristic equation has this property if mu of lambda 0 is smaller than 1. What is this mu of lambda 0? Is this expression. We will find it several times during the word as I teach. Let us see auxiliary theory. We will consider lambda 0 as a positive real root of the characteristic equation with the property A, as you see here it is that property, and we will have this function beta of lambda 0 given by this. So for any initial condition, what we will have? We will have that lambda 0 minus n, it will multiply by the solution is equal to this value. And now you ask, what is this L? Beta is here, but L is this big function, this big expression. L will depend on lambda 0, here it is, and depends on the initial condition. So for each initial condition, I will have here a solution. However, the importance is the limit equals to this. I will show you a draft of the proof. The property A, what say? The property A say that mu of lambda 0 is smaller than 1. However, I have here the function beta, where the modulus, it will be this, and it's smaller than this. Triangular inequality. very easy to be applied. However, when I look to here, what I will have? I will have exactly mu of lambda 0. It is here, the property A. So I know that the modulus of beta is small than 1. In the other words, I can conclude that 1 plus beta 0, it will be more than 1. It will be positive. What we can do with it? Let us see. But we will take this expression. Notice that in our equation, when I pass for first member the sum, I will have this expression. I will do a change of variable. So here I don't have the equation. I have only the first member when I put my equation equal to 0. And I will do a change of variable. What change of variable I'm doing? I'm doing lambda n equal to lambda 0 minus n multiplying by xn. So when I apply this change of variable in our expression, I will obtain this. Now we need to do several calculations to obtain what we want. First of all, we will develop this part. I will put in evidence lambda 0 n, and since lambda 0 is a positive real root of the characteristic equation, what I will obtain? I will obtain this. Just some computation that I don't put here because it's very long. So, what can I conclude after that? I conclude that if x is a solution of this problem, then epsilon n that I defined previously, it will be solution of this one. So I establish a connection between these two equations. When I use the initial condition of x to define the initial condition for epsilon, I will have my problem completely developed. And what I will get that epsilon n, it will be this expression. And here it is the L, that L that appeared in the limit. Now, I will do another change of variable. I will say that the n is epsilon n minus this value. So, the n, doing the change of variable, it will be given by this. And using the initial condition once more, the n will have the initial condition given by this expression. Now the question is the limit of the n equal to 0? Because if it is equal to 0, what I will have? I will have the limit of epsilon n, it will be this. And I will find what I want. So let us see. First, we will define m as the supreme of this modulus of this difference. More, the initial condition of the n given by this implies that module of z is smaller than m, evidently. So, a couple of computations, and we will find the modulus of Zn small than this expression, Green-Blatt inequality, and this is small than this. Wow, I look to here and I see here what? The property A, once more. So, here it is, Zn in modulus is no larger than mu of lambda 0, m of lambda 0 c, initial condition. Well, when I do this several times, what we will get? We will get that the model of Zn, it will be no larger than mu of lambda 0, v, because I did it v times, multiplying by n. I have here everything that I need. Why? Because mu is smaller than 1. If it is smaller than 1, what happens when I keep doing some and once and another time this this method? I will find that the limit is 0. Great, is what I want. So now you are ready for the main theorem of the stability. In main theorem of the stability, we will have what? We will have lambda 0, positive real root of the characteristic equation, just before, like before, and we have the property A, just we get before. Now we have beta, just like in previous one. So for any phi, I know that is set. I have the modulus of xn no larger than n lambda 0. Here we have the initial condition and we have lambda 0 n. The question is, what is this n? This n is this expression, where I have here the property A, saying that this mu is smaller than 1. I have here beta. I have here everything. But you can ask me, and the k? The k, it will be the maximum between these two values. So, for any phi, I will have this. More. What can I say about the solution of this mixed type difference equation? Well, I will have uniformly stable if lambda 0 is 1. Look to this, evidently. The proof is not so evident, but we can feel the result and understand the result. And for that reason, I will prove this expression. However, here is a couple of steps, and we can understand easily, so I will ignore the proof here in my presentation. The solution, it will be uniformly asymptotical stable if lambda 0 is smaller than 1, of course, because if it is smaller than 1, in the limit, this goes to 0. And it will be unstable if lambda 0 is more than 1, because this jumps to infinity. So, to the graph of the proof, what we will do? We will take L. We saw before what is this L, and here it is again. From here, when I do the model, inequality, singular inequality, I get this expression, a couple of calculations, computation. What we will find? We will find that this is smaller than this big expression. But what we know that the maximum of lambda 0 and lambda 0I is no larger than maximum between 1 and lambda 0 L1, lambda 0 L. In this is no larger than kappa lambda 0. This was I between 1 and L. More, the maximum between 1 and lambda 0 minus G plus 1 is no larger than the maximum between 1 and lambda 0 minus m. And this is no larger than kappa 0. So I can use these inequalities here and easily we obtain this expression. Look here, the property A. I told you property A appears several times. And this means that model of L, the norm of L, it will be no larger than the norm of phi multiplying by 1 plus mu k both in lambda 0. So, taking m no larger than this expression and using what we know now about L, well, we can obtain this. M no larger than P lambda 0. Here we have a nice coefficient, and here we have the norm of the initial condition. So, exponent that you saw before, it will be no larger than n of lambda 0 norm of the initial condition. What this means? It means that it is clearly written, and this means that xm in model is no larger than the n of lambda 0. Here it is the initial condition and lambda 0 in n. Just what we want. From here, we have an additional lemma. On this additional lemma, we will consider R as the maximum between L and P. So, if this, we will have this expression bigger than 0, this one bigger than 0, and this one no larger than 1. Positive, but no larger than 1. Now, with all these conditions, what we can get? In this interval, the characteristic equation has a unique positive root, and this root satisfies the property A. As you can see, the property A appearing everywhere. So when we have the property A, it's like to have a treasure for this result. A draft of the proof, we will define f as this function with lambda just in that interval that I saw you before. What is f of r dividing r plus 1? It is, well, the first condition says it is positive. Look, minus, 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 so this is negative. F is negative. Here, what we have? We will have this expression, but using the second condition, what do you have? We have this positive. This is positive. So, f is continuous. On these intervals, it's negative, and after it will be positive. Well, a root we will have a root of this, it will be 0, or in the other words, the characteristic equation will have a root on this interval. But it's only 1. How can I be sure that it's only 1 and not 2, 3, something? We have a third condition to be used. So, we do the derivative of f, and what we obtain? We obtain that the derivative of f is more than this. But this is the first condition. So, in that interval, I will have a function with a 0, and that function is increasing. So, I only have 1 0, just like we want to do. F1 as a unique solution in this interval. In the other words, the characteristic equation we will have on a positive. But that's not all. We have more to do. So, taking the property A, because we want to know if lambda 0 verify the property A. Yes, it will verify. What we have here it is the expression for the property A is equal to this one, and it's more than this. And it's more than 1. Why? Because I have this condition. The first condition says this. Now, using the lemma with the theorem, I will obtain a very important result. Once more, I have same R, maximum between L and M, and the same 3 conditions. With these 3 conditions, I know that the characteristic equation has 1, 0, unique, positive, and it verifies the property A. So I can get more about my theorem. And for that reason, I can get a corollary. The solution of this equation is asymptotical, stable if this sum is negative and unstable if it is positive. That's all. As you can see, with this corollary, I can obtain a very easy way to study the stability of my problem. Let us see examples. Examples help us to fix the results and the importance of the results. We will consider this difference equation. What is the characteristic equation? Is this one. So I can rewrite this as a polynomial. And what root has this polynomial? The characteristic equation is here. Every root, lambda 1 equals 1, lambda 2 don't matter because it's negative, lambda 3 and 4 don't matter because it's complex. So I only have one solution important for me. It's positive. Easily, we can see that it verifies the property A, and so by theorem, the solution is uniformly stable. Example 2. This equation is very, very easy. Here, it is the characteristic equation. Lambda 1 is 2 over 15. Lambda 2 is 2 over 3. Wow, I have two possible solutions. Both are positive, but both are verifying property. No, this one don't verify the property. However, this verifies. So I can use this equation and by this solution, and by theorem 2, the solution is uniformly asymptotically stable. But if I want to use the corollary, corollary is so nice. When I want to use the corollary, what I will have? I will have r equals 1, and this sum is negative. Well, what can I conclude? Exactly what I know before. The solution is uniformly asymptotically stable. As you see, we have here a very interesting corollary. I really like it. Now, oscillatory behavior. Let us do a small introduction, because for the asymptotical behavior, we will do a small change. And what is a small change? A small change, but it's very important, as you can see in the end of the paper, and easily we can understand. Here, the coefficients are not real numbers, are sequences of real numbers. Each one of them is a sequence. We change a lot of things. And here, the delay and advances is not n minus a number, n plus a number. No, I can have here a logarithmic, for example, and we will see why it can be. I don't have any example with that, but it can be. I can have n squared for here, or the exponential. I can have a lot of things, not something so linear, like n minus 1, n minus 2, n minus 3. Your question, I can imagine, should be, why not to do the stability for this case? Unfortunately, until now, it's an open problem. It's very difficult to study the stability when we have here sequences and here something that is not linear. It's an open problem. Who knows, in the future we can do it. Who knows, someone of you can help me and help my colleagues do it, our colleagues on this case. So on this problem, Here it is the delay term. This delay is positive, of course, this sequence is positive. More than Rn minus 1, and for that reason is a delay because it's more than n, and more. The limit must go to infinity. You see why I told you, oh, here I can have a logarithmic, for example? Yes, it's verify this with no problem. It's enough to have n more than 0, more than 1, and immediately all of this is verified. And for the advances must be positive, and of course that now you can imagine that the advance must be more or equal to n plus 1. So here is more than n, here must be more than n. And of course the limit goes to infinity. More. P, I, and T, G are real. A solution of this problem is said non-oscillatory if it is either eventually positive or eventually negative. In other words, what it means? It means that I have the solution, and after an n 0 and 1, after one order, the solution, it will be always positive or always negative. If my solution jumps between the positive and negative values, I will say that it's oscillatory. So when I have different equations, I will have a set of solutions. If all solutions are oscillatory, I will say that this equation, it will be oscillatory. Of course, a set of solutions depending on the initial conditions, as you know. However, if it's enough to have one non-oscillatory solution, and I will say that my problem, my equation is non-oscillatory. So to be oscillatory, all solutions will be oscillatory, and for non-oscillatory, it's enough to have one non-oscillatory. First here, these sequences are non-negative, and the limit superior of this sum is more than 1. Third question, I do this and I imagine what is in your head and what questions are you thinking now. I can imagine that you are asking, okay, what is this P? What is sigma? What is tau? It don't appear before. Sigma is the minimum of the advances. Tau is the minimum of the delay. And T is the sum of all coefficients of the advanced side. So if it is more than 1, I can guarantee that my equation is oscillatory. So all solutions will be oscillatory, independently of the initial condition. As you can see here, the initial condition is not important. But what I want, what I know is my equation is oscillatory. Let us see the Xn is non-oscillatory. Well, if it is non-oscillatory, we can imagine is always positive. After an order, after n equal to something, my solution it will be always positive. If it is always positive, easily we can see that the difference operator it will be positive because P is positive, non-negative, E are non-negative, so we will fix that it will be positive and X is positive. So this is positive. If it is positive, my solution Xn will be increased. If it's increasing, when I do the sum in both sides of my equation, the sum between tau and sigma minus 1, I will get this. If putting the parts of x and b increasing, I can obtain this. How? Well, I will use factor to be increasing. I will maximize. I will pass everything for one number, and what I will get? I will get that this is negative. Well, how is this possible to be negative? If p, each coefficient p and t are positive, this is positive plus 1 positive. X is positive. And one of the conditions of theorem, the assumption, main assumption of this theorem is this is positive. What I get? Yes, I get a contradiction. Here it is. Because this must be positive. So if I have a contradiction, what this means? It means that xn is a shape. Let's see the corollary. The corollary comes for this equation, where here I will have n minus tau I and n plus tau g. Or if you want, you can consider here a real number, here a real number, and we have a positive one. Now, next. Very well, as I told you before, this equation is a little more stimulating than the before. Why? You see, n squared plus 1, n squared plus 2. In the beginning of work, when we studied the symptotic behavior, we cannot have this squared. Here we can. What is C? C is E over ln of 4. It is our first delay, second delay, the advance, and the advance. Now, we will have tau and sigma. Here we have a misprint. Here it is a minimum, but it will don't change the rate of. Here should be the question is this limit more than 1? How can I write this limit here in this equation? In this equation, this limit will be the sum. It will be, and it's the limit of this sum that I want to know if it is more than 1. Let us rewrite, and here it is, our question. Well, here we can prove that this sum is more than this sum of the integral. And this integral is very easy to be solved. So what I will have the sum more than this C1 logarithmic of a coefficient of logarithm. And you ask me, okay, it's more, but why? It's more because I'm using this property for monotonous functions. And it's using exactly the same that I can see that at the same time that this sum is more than this, it will be less than this. So my sum is between two values, two sequences. However, when I look to this sequence and I look to this one, I say, yeah, it's two sequences, but the limit is the same. Yeah, the limit is the same. And this is very good because the limit is the same, is more than 1, and this way I'm sure that by theorem all solutions of this equation are sure. Let us now see out the theorem 1. In theorem 1, we have this. Now, the question that I put to myself when we did this work, it was, can I improve this inequality? Can I add, or what should I do to improve this inequality? I will establish a second theorem where I say that the delay and advances, all of them are increasing. And that expression, it will be replaced for another one much more nice. Because if this limit is more than 1 over e, notice that is not more than 1, it's a little less, so I can have a value acceptable sooner, then my equation is assured. And this is really good. Let us see the proof. After we will see the example to fix this result and see how it is nice. First of all, we will define this sequence, CG of n. From here, easily we can verify that CG of n is bounded, and it is bounded by 1 over 4 and 1 over e. You see where is the 1 over e? It appears here by the first time. This is our assumption, and it's normal to be 1 over e because from our assumption, we can guarantee that this sum is more than 1 over e plus something. And with these two conditions, what I will have? I will have that the sum of this coefficient is more than d, and this d is something more than 1. So xn is increasing. If it is increasing, I can establish these two inequalities. X of the delay when divided by xn plus 1 is more than 1, and the x of the advances when divided by xn plus 1 is more than 1. So I will take my equation and I will divide everything by n plus 1. For what? We will see later, because now we will rewrite xn divided by x of the advances as a product. And from this product, I can be sure that our coefficient is no more than this. And what can I do with this? I can use the inequality of arithmetic and geometric mean to establish this inequality. Wow, something with a good look now is huge. But why I use something so complex? Because I will use this inequality. This inequality is valid when epsilon is between 0 and 1. So it's using this that I can be sure that x dividing x of the advances dividing by xn is more than this. Now, with it, and what we saw in the beginning, the x of the advances dividing by xn is more than d, and this d is more than 1. What I did now, I can repeat several times. And when I repeat 3 times, I will obtain this. On the other hand, I will take again the equation divided by xn plus 1 that I did before, and I will see what I can do with it. Well, first of all, I know that this is positive because x is positive, so this is positive. And of course, that's what I will get from here. When I ignore this term, I will have 1 minus this expression. It will be more than 0, of course. So this is more than this, so it's more than 0. Good. But from here, I obtain this value, x of the advances dividing by xn. When I multiply by t, I obtain something smaller than 1. Now, I will consider a sequence going to infinity. I'm sorry, here is plus infinity and not n. it was a second misprint of the here we have the x of the advances dividing by x of the sequences, and here the advances are applied by the sequences. And when I use the previous knowledge, I know that this is smaller than plus infinity. In the other words, this limit exists. Well, wait, something here is strange. Why? Because before I told that this coefficient is more than the c. In b is more than 1. So when I do infinite times the same computation that I did before, this goes to infinity. The limits don't exist. So what is the problem? The problem is I consider a non-oscillatory solution when the solution, in fact, is an oscillatory solution. My problem, my equation is oscillatory. So it is with our theory. Recalling the corollary, what changed here? Here it changed something very easy because we don't have the problem of the increasing sequences. We will have just and the limit inferior of this more than 1 e. So my problem, my equation is oscillatory. Example time. Here it is an example. So nice, so easy. Here we have as delays n minus 1 and n minus 4, the advance n plus 1, n plus 3, and the coefficients are constant. So what I will have? 2 advances, and if b is more than 1 over e, notice that here I have several limits, because for each g, I will have a limit. So the first limit, it will be 17 over 15e, so it's more than 1 over e. Here I have 17 over 5e is more than 1 over e. So by the second theorem, all solutions of equations oscillate. Or we can use the corollary. Both of them can be used. First theorem. We have now non-positive sequences in our coefficient. Until now it was non-negative, now are non-positive. The proofs are very similar, and for that reason I will not do it. However, I will show you the result. Here, what we will have the equation oscillatory when here this p means the sum of all coefficients and the coefficients of the delay files. So on the if this limit is smaller than -1, then our equation is oscillatory. The corollary is similar. We have the limit small than -1, and our equation is oscillatory. For the example, here, look how this example is nice. What I have here, I have the entire part of 0.5 n, and here n 0.5. So as you can see here, I don't have something so linear in the previous one. I have something that only can appear on this problem. I cannot take this equation and use it in my first part of my file. It's not possible yet. In the future, I believe that it can be. Me and Professor Ali Fuat, thanks if someone can help us. So let us see what we have on this problem. Well, we have here two constants, 3 over 2 logarithmic of 2. We have first delay, second delay, first delay, first advance and second advance. Tau is this value, sigma n plus 1, and the question is this value smaller than -1? When we write for this equation, this sum, what we will have this. Let us analyze. So the question is this smaller than 1 in the limit, of course? Yes, because this sum is between these two values, using same inequality that we saw before. And here it is the limit, because both of them have the same limit. An easy computation. So the limit is in fact smaller than -1 because it's -3/2. So by the theorem 3, all solutions of the equation are shared. Now, recalling again theorem 3, and what we will change here to improve our result or to have a different result depending the problem. We will establish the fourth theorem where we consider the PT, so the sum of all coefficients of the delay part, that sum is between -1 and 0. So I have replaced this condition by this one. As you can see, I'm near of 0, so I have a bigger range for the limit, not more than -1, but smaller than -1 over e. So our equation is a corollary. Now, the corollary, it will be very easy because it's enough. That's the only thing that changed. So, one more example. Here is the delay, second delay, advance, and advance. We have the two delays because it's most important for here is the delay. We will have the limit to compute, and here it is. The limit is -7/6. E is more than -1/e. And the second limit, it will be -7/3e is less than -1/e. And see this, we can conclude that all solutions of our problem, our equation, socialize. And with this, I thank you very much for your attention.
Thank you very much, ma'am. Very informative session. We have some queries raised by the participant, ma'am, in Q&A. With your permission.
Sure. I'm trying to change here my screen again.
Okay.
Oh.
I request Dr. Vishnuvardhan SV, Assistant Professor, Department of Mathematics, GSS, to read the questions. Over to Vishnuvardhan.
Sure.
Nenu video chestunna.
Yeah. Thank you, Professor Sandra Pinalas, for your excellent talk. From the participant side, there are some doubts, Professor. With your permission, I am going to share a few doubts in the form of questions. So these are some questions, madam. Not clear. Question is like this, madam. This is the question raised by Syed Basha. Respected Professor Sandra, if possible, can you please explain at which situation this concept may be utilized. How to create a problem statement including the explained concept.
So I'm not sure if I understand very well the question. I suppose that you are asking
Application.
some,
That is one of the
application
application. Madam.
about
Yeah.
it. In the literature, we can find some applications of this problem. I remember, for example, a paper that I read some time ago, where we have a physics application of this. And what was the problem? It was a mixed type. In that case, it was not a difference equation, it was a differential, but the question is the same, is to use the past and the future. And on that problem, what they explain and use some things like an equation like this, it was when is the mechanism of our brain. When we think to do something, what happens? In our neurons, the information arrives. For example, let me see how can I explain it easily. You want to move your arm, okay? Want to move it. The information goes to your brain. So you will conjugate your past information and your future action. So you will conjugate in your brain the information between the position of your arm is something that you have now in the information that you have now. It arrives at your brain, and after your brain commands your arm saying, move it. So you have both information in your brain, and that information jumps from neuron to neuron. And there, when you do a model for that, you will have a differential equation with the past and the future. The past is the position of your arm, where it was, and the future is where it will be next. As you can see, something very, very fast, because when you move, you don't stop to think, oh, okay, let me see what my brain says. If you are okay, of course. But this is one of the applications. In economy, this is very, very important. Perhaps the economists should use it more. Why? Because they have the information about a sale of the product, how it is. I have a product and what I want to provide from there. So I must have the information of the market before, how the people are buying my product and what I want. So in economy, the past and the future are very, very important. For example, I don't know if I was clear.
Yeah, I think it is clear, madam. Thank you, madam. So the next question is by the same persons, Syed Basha. How to connect this concept with the fractional differential equations? That is the question, madam.
With the differential equation, we want to know how to connect the difference and differential equation.
Fractional differential equation, madam. Recent trend, that is fractional differential equation.
Fractional. I don't work with fractional differential equation. I work with ordinary differential equation. And it's something that I really like, is to establish a connection between both of them. And on this moment, I don't have any work doing the connection between these two words, because this paper, these results that I just show you, one of them was published a few weeks ago, and the other one was accepted but not yet published. So I have no time yet to take this problem, and now we will develop this to differential equation. But Notice, is an ordinary differential equation, not fractional, because I don't work with fractional differential equations yet.
Yeah, thank you, madam.
However, who knows if you can do it together.
Yeah. Another question is from Maria Das. Yes, I think it's asking as, kindly give one open problem in this topic, like that.
Open problems, I have a lot of open problems. What I need is time to work. If someone very interested about it, to work. So if she is interested in my open problems and she is interested to work, really work, I accept. Let us do work. I have a lot of them. I don't have time, but work, I have a lot of them.
Yes, madam. Thank you, madam. Another one question is there from Professor Pradeep Kumar Radhakrishnan. He is asking like this, madam, regarding the oscillatory behavior of forced second order integro-differential equations, integro-dynamical equations on time scales, considering results on the continuous and discrete cases, can they be applied to Volterra integral equation on time scale?
Yeah, we can apply this to time scale. The problem is exactly the other. It's time to do it. But it's possible to apply to time scales, of course.
Thank you, madam. Another question, our panelist member, CSK Raju sir is going to ask.
Myself, Dr. CSK Raju. In auxiliary theorem, you have mentioned the change of variables, y of n is equal to lambda power minus n into x of n. Why we need to take any specific reason for that? If suppose if you take lambda naught power n into x of n, what will happen? Is there any?
I'm so sorry, I didn't understand very well your question. Can you repeat, please?
Yeah, sure, madam.
Question of sound.
In auxiliary theorem, change of variables, you have mentioned y of n is equal to lambda naught power minus n into x of n. Is it clear? In the change of variables, madam. When you are transforming the one domain to other domain, I guess. I think you are substituting the substitution values.
Substitution of variables. Yes, it's possible.
Yeah, if you take there, you have mentioned lambda naught power minus n, right?
Wait, we are talking about one of the images that I show.
An auxiliary theorem.
Are you talking about the proof of the theorem?
Yeah, in proof of a theorem.
When I do the change of...
Yeah.
Oh.
There you have mentioned the change of variable lambda naught power minus n, madam. My question is why minus n? If you take positive value, what will happen?
Let me see here. I'm trying to find now the proof and share again my...
The starting slides, madam. Yes. The starting slides.
Here it is. Let me share with you again my screen with you. Here it is. Is about this change of variables?
Yes, madam.
Okay.
Yeah, exactly.
Okay.
Why here minus
so tell me.
Negative value?
Yeah.
Yeah.
Minus n.
Yeah, third step, madam. Third step. Yeah, you have kept cursor, madam. Same. Yeah.
Yeah.
Yes, madam.
We change. It's okay now?
Lambda is a positive root of cat.
No, I'm asking about minus n, madam. Okay.
This minus n is because of here. We need to have that minus n because to have here 1 over lambda 0 for the initial condition. Before that, we need it. And it's the only way to work.
Okay, madam. Thank you.
Welcome.
Thank you, madam. Thank you for clarification. Over to Sasikala, madam.
Thank you very much, ma'am.
Welcome.
Thank you very much, Professor Ayman Badawi, for making time to attend this session.
Oh, thank
And
you.
thank you, Professor. Sir. Welcome, sir. Thank you, Professor Sandra Pinales, for an excellent presentation on the behavior of the solutions for linear autonomous mixed type difference equation. We are happy to have you here, ma'am, and your presentation is very helpful and valuable to the participants. And we received more messages in chat box from the participants, ma'am. They are very happy with your presentation. Once again, thank you very much, ma'am.
Thank you very much. Thank you for the invitation. I wish you the best. And I hope one day to meet you there in your country, in your university.
Okay, thank you, madam. Madam, participants are asking PPTs, ma'am. With your permission, can we share it?
Thank you. It
Ma'am?
was a pleasure.
Participants are asking PPTs, ma'am.
Oh,
If your permission, we will share it.
Oh, to share. I will send you.
Okay, okay. Thank you, ma'am.
I send you the results and the paper where the results are published. No problem. Okay?
Oh, okay, thank you, ma'am. Thank you very
I
much,
can
ma'am.
send you some material.
Okay, thank you, ma'am.
Thank you so much, madam.
Thank you. Thank you for your invitation. It was a pleasure. And anything that you need that I can help you, just tell me, and it will be a pleasure to help you or to help any participant. Now we have here some open problems, so why not?
Yeah, sure.
Yeah, sure,
Yeah,
madam.
sure, madam.
Anything is there, definitely I will forward
forward
you.
your mail.
Thank you.
Thank you, madam.
Thank you. Bye-bye.
Bye, bye. Yeah, you can please.
Dear participants, we have already posted the feedback form in the chat box. Please fill the Google form. So if you are filled, you can leave the session. Exactly half an hour we are going to accept the responses. Then after we will close.
Sorry, coming to the tomorrow session, Professor G. Raj Chikit is delivering the talk on neural networks and deep learning. Tomorrow session starts at 2 p.m. onwards. I request everyone to join 10 minutes before the session. I request everyone to fill the feedback form which is given in the chat box. Feedback form will open up to 3:30 only. Yeah, I much better. I done.
Okay, have a good day, everybody. This is Ayman Badawi.
Yes, sir.
Yes, sir.
Yeah, and tomorrow your talk, it will be during my the class I teach.
Okay.
So I will try maybe to come for 20 minutes.
Yeah, sure, sir. No problem.
Okay, I'm sorry.
Yeah.
All right, have a good day.
Thank you so much, sir.
Thank you.
Pleasure, sir.
Thank you very much, sir.
We are going to end the session. So after 10 minutes, So Google form is available. So in the chat box, please fill it, and the response is we are going to receive up to half an hour only. After that, we are going to close the response to receive.